accepted.
All right, let's get started. Welcome to the session on design patterns revisited in modern Java. My name is Venkat Subramaniam. We will talk a little bit about some of the things we can do with design in general with more recent versions of Java. I'll cover a little bit about things we could do in functional programming, Java 8 and onwards, but a few things since then as well in more recent versions. Well, first of all, of course, design and design patterns. Generally speaking, I would say programmers, especially Java programmers, are always fascinated by design patterns. We are drawn towards using patterns. But in my experience, what I've noticed is design patterns are not as much a great design tool as they are as a communication tool. I find it extremely helpful to use them for communication, to convey to my colleagues how I've approached a design rather than simply applying it as a design itself. And the reason for that is I've seen a lot of code being created in a very complex way because programmers are eager to apply a design pattern. And unfortunately, when a pattern is used incorrectly, it can actually complicate things quite a bit. So oftentimes, what I would like to do is to look at a problem, work through it, have a design evolve and emerge from it, and then, of course, relate to, oh, look, this design is gravitating towards this particular pattern. But anyway, having said that, I want to talk about a few different patterns that we can make use of. But I want to first start with maybe what's an anti-pattern rather than a pattern itself. So let's think about this a little bit, if you will. So let's say for a minute we have a class called person, and let's say this particular person class contains a pet, and maybe this person only has one pet. Let's start with that first. Now I'm going to provide a function. Let's call this as a getPet, which is going to return the pet for this particular person. So I may be saying return pet over here. Now, of course, one of the problems in this particular code is, what if a person doesn't have a pet? What's going to happen? So potentially, you might do something like this in your code. So you could have maybe a person. So you could say, for example, a person.getPet, and you might even say getName. You want to know what the name of the pet is. Now, clearly looking at this code, one of the problems you're going to potentially run into is, what's going to happen if the pet doesn't exist? Well, that may end up with a null pointer exception. Anyone here who enjoys getting a null pointer exception? Not really, right? We all don't like null pointer exception. We cringe when we get it. And if you think null pointer exception is not really that terrible, you should talk to my good friend Brian Sledden. He was at a hotel and he turned on the TV, and literally the TV displayed a null pointer exception. Forget about horror movies to watch after that, right? That's kind of scary to get that kind of an exception on the TV. Clearly, the programmers who wrote the code did not handle the exceptions properly. So I actually am not a fan of null at all. So I would actually generally say that null is a smell, and I want to avoid null as much as I can. Well, in this case, of course, as we know in Java, we don't want to get into an accidental null pointer exception. That's the whole idea, is we don't want an accidental null pointer exception. So a recommendation in Java is not to return a pet like that, but instead to return an optional of pet like so. So the idea behind this is, of course, if the pet exists, we return it. If the pet doesn't exist, we return an optional which contains an empty versus an optional that contains the object. Now, of course, this is intended to really eliminate the accidental null pointer exception. However, I was quite shocked when one programmer decided to return null from here. So, a bad idea. So my recommendation is never you should try to foolproof something because there's a bigger fool who comes along all the time. So there's no way to eliminate these kinds of things, though it's written with good intention, so definitely don't do that. But having said that, though, when is it a good time to use optional? And I would argue use optional only for return type. I would say return type when the object may or may not, if you will, exist. Having said this, let's say, for example, we have a function called a setPet. And the question here, or maybe you want to have a function called, change a pet. Maybe you want to really change the pet that you have, and you're going to take a pet as an argument. So the question then is, should we really take an optional of pet over here, like so? And the answer is, I would simply say, please, no, don't do this. The reason this is not a good idea is, think about the person using this particular function, if you will. So, for example, if you think about it, you may write the code, and maybe your intention is to set a new pet. You might say a pet, person dot change pet. And you might, in this case, say optional, of, maybe you'll send buddy here as an argument. But what if you don't want to really send a pet? You would have to then say a person dot change a pet, and you're going to say optional of empty. And this is really a terrible code. And you ask the question, how does the user, how does the user of this code feel? That's a question you want to often ask. They're not going to feel happy and excited because that's so smelly to write that code. Not a good design at all. So what's going on in this particular case? Your goal, of course, is to say that I want to change this pet, but sometimes I may want to remove the pet. So my recommendation is be intentional in your design. So this is something we can do to really make very explicit what your intention is. It doesn't give any ambiguity as to what you are trying to do. And second, it also makes it easier for our users to write the code. So my recommendation is don't do this, but instead what you can do is simply say, for example, change pet, and take a pet, maybe a new pet that you're going to provide right here, and provide the function, but also provide a remove a pet, if you will. And that way, it is extremely clear what your intention is. So in this particular case, what you would do is, when you want to really change the pet, you would simply pass a buddy to it. That's much easier than optional of buddy. And of course, when you want to get rid of the pet, remove the pet rather, you can simply say remove pet and call that, and that becomes a lot easier as well. So the intention is very clear, the code is clean as well. So general recommendation is use optional as a return type, but again, when you don't expect a certain data to be present, but don't use optional as a parameter to a function, because if you use it as a parameter to a function, it really makes the API clumsy. Now, having said that, this is about a function that a human is going to use to call it. Sometimes people ask me, well, what if I'm defining a controller in Spring or other framework? Well, your controller is not going to be used by a human directly. There is a machine that's going to take the input and call that function. We humans are feeling that thankfully machines don't, so it doesn't matter in that case. But if it's a human callable interface, be gentle, be kind to them, be humane to them, and so don't take an optional as an argument. That is generally a good practice to avoid it as much as we can. So that's about a pattern, an anti-pattern when it comes to using optional. Now, it turns out that we've been using certain patterns over time, but I want to say that this is a way to think about it. When it comes to design patterns, I want to say the more powerful, you would say powerful language, let's say, is, the less we talk about, in general, you would say, patterns. So essentially, the more powerful a language is, the less we actually talk about patterns. Now, the reason for that is, the powerful languages will fold into the language as features what we often celebrate as patterns in other languages. So, and also I would argue, when the language evolves, more and more things can become natural in the language rather than standing out as a pattern. Let's think about this with an example to think about the strategy pattern. I'm sure almost everybody has used the strategy pattern, but what is your memory from the strategy pattern? You create an interface, you create a bunch of classes, and then you can use any of those classes. You end up creating a factory, and while you're doing this, you tend to forget why you started doing this in the first place. There was a lot of code you had to write. It becomes verbose over time. But it turns out a strategy actually is just a snippet of a function. But why did we really create interfaces and classes to begin with? Well, that is because back in time, Java had this ideology that everything should be objects. Now, that changed obviously in Java 8, where we can use lambda expressions, and so functions are beginning to look a lot like first-class citizens in Java, but before Java 8, that was not the case. So let's think about a little example to, consider this for a minute. So imagine you have a list of numbers, maybe, prices, some values, whatever that could be, and maybe you're at work and your colleague says, I want a total values of all the numbers that you have. So maybe in this case we can say numbers is equal to, let's say list of, let's go ahead and take a list of numbers 1 to 10 to work with it. So given these numbers, your colleague says, find me the total of all numbers. But that's on a Friday afternoon. You've been talking about this very exciting get-together you're going to have with the long-time friends you have not seen in years, and you've been talking about this, so your entire mind is that party you're going to go to that evening. So you have really no clear intention to be writing this code, but as life has it, your colleague wants the code, so we have to write it, right? So what are we going to do? You could say public static, let's say total values. You can take a list of integer, we'll call it as values like so, and let's keep it really as a very straightforward code here. We'll say a result is equal to 0, and I want to return the result from that call in this particular case. So the result is a 0 right now, as we can see. But what I want to do, though, is to take the values, so we can say an element coming from the values, if you will, and we can simply go ahead and say result plus equal to the element, and we can add those values, so we got a 55 as a result. So you got that code working, you commit it, and before you could move on, your colleague says, I also want a function to total all the even values in this collection. And you're like, gosh, I got to write another function maybe. And you ask your colleague, do you really want the total values and also the total even values? And your colleague says, yep, I need both of those functions. And you look at your clock, it's getting late to go to the party. You much rather be there partying than be at work. And then you think about it and you realize it's not really that hard to write that function. And you tell yourselves there's got to be a reason why they created copy and paste, right? I mean, if nobody should use copy and paste, why would they even have that as a feature? In fact, it's so cool, they even have a shortcut for it, right? A Control-C and a Control-V, how cool that is. So you can just, copy that code really quickly, and you can simply say, here is a total even values. And you can say in here, if the element that you're interested in is an even number, then you want to total it. Otherwise, you simply want to ignore that particular value. So now that you have that working, you see that the total even values is working. But as fate may have it, your colleague now says, I need a function to total all the odd values. And you know that copying and pasting a code a third time is an act of criminal negligence. But nobody is looking, it's a Friday evening. Well, that's not going to really take us much far, isn't it? So what can we do to eliminate this kind of duplicated code? Well, as it turns out, if you look at this code, whether the value is an even number or the value is an odd number is really a strategy. That's what it really comes down to. So let's undo that change and pretend we never wrote it. So back to this total values function, your colleague now says, I need to be able to total values and even values as well. So now you can say, before I make a change to it, I'm going to perform a little bit of a refactoring. So we are going to come down here and say, bring in a function.predicate as a import right here. And we can then say here comes a predicate of integer, and we'll call it a selector, if you will. So we are receiving a predicate as a second argument to the total values. Then we can come in here and say that if the selector test on the given element E is equal to true, then we want to add the value not otherwise. So, and of course, as a final change in here, we can come back and say, given an element, simply return a true, because we want to accept all the values given. So now that with the change, of course, what we can do here is, we can say, given an element which is an even number, we can perform that operation. Now, of course, if your colleague wants a function to total all the odd values, you can ask them to go write it themselves. And as an example here, you could even do the following, where you can say a sample is, let's say, odd. And as a result, you can go back here and write a separate function, if you will, which is a Boolean, we'll say is odd, which takes a number as an argument. And we can simply say return number mod 2 is not equal to 0. And so we can write that function separately as well to total odd values. So as it turns out, the lambdas are really, so lambdas are great for use as a strategy. So essentially you could say, write your functions, whatever the functions do, you can capture the common algorithm or the common code within that function, but any variations you want to provide, you can provide them either as a lambda expression or as a method reference, like so. So you could create a separate library of those strategies and simply pass those strategies into your code. So using the strategy pattern becomes almost trivial, given the fact that we can pass lambdas around as functions in code, and as a result, we don't have to waste our time creating classes and creating factories, and so it becomes a lot more easier to work with it in general. So that's an example of how we can use the strategy pattern as well. Now, one other thing that I find to be intriguing is to really look at default methods as a way of developing a factory method pattern. So a factory method pattern can be, remember what a factory method pattern is. A factory method pattern is where a base class delegates to a derived class the specifics of the objects it wants to use. So typically when you use a factory method pattern, you have a base class which contains all the common functionality, but there are a few objects that you want to vary that it's going to use. So typically the base class functions will call a create function, for example, but the create function is not implemented because your base class is often written as an abstract class, and then you derive from your base class and you override those create functions. But with interfaces and with default methods, we can achieve a very similar goal as well to enjoy the factory method pattern. So let's take a look at an example. So let's say we have a person. We'll say person is equal to new. Well, in this case, I want to create a person, and I say person.play, let's say, is a function I want to call in here. We'll come back to fix this in a minute, but I want to start with an interface for a person like so. So in this case, the person is an interface, and within the person, I'm going to say a default void, a play method I want to create right there. So what does the play method do? It's going to say maybe a play with, and it's going to use a pet as an argument to play with that particular, the person to play with the pet. Now, clearly in this case, this is an interface. If it was written as an abstract class, you would have provided a field which would be a private pet and a pet as a field, but you cannot really do that with an interface because interfaces cannot have, non-final fields. That's not permissible. However, what I find it to be really useful is to really provide a function here called getPet, which, as you know, is an abstract method in an interface. You haven't implemented the get method, so getPet method. So this becomes your factory method, if you will, in the factory method pattern. So then what you can do here in the code is to simply call the getPet method right here, like so, for example, and you can say getPet, and you're able to use that pet in here. So you can use this approach for various different things. You could write an interface that captures maybe an order processing, but the payment method may be created by one of the derived classes. So you could really use this idea for various things. So the methods that are common can be in the base interface. And then, of course, the abstract factory method, rather, can become an abstract method that you can use right in there. So now let's get back here, and let's say we have a dog person, a person who really enjoys the company of a dog, let's say. So I say a dog person is going to implement, in this case, a person, but what we are going to do is to implement this method right here. So we have a public, and we can say, a public method, we can say a public, we'll say in this case a pet, we'll say getPet. So obviously in this case, what are we going to do with the pet? You could be returning maybe the dog, which is the pet, you can say pet. And this could be, for example, a person who takes a pet as a dog maybe as a pet. So this could be a dog that's coming in. And you could say, save that away as this.pet is equal to, you could say a pet, and you could use it like so. So this could be a nice way for you to receive the pet. You could have a private pet, and you can store it. You can even potentially write this as a record if it makes sense. You could do that as well. So in this particular case, you're returning the pet from this particular object. So basically, the idea here is you could have a pet, for example, as a class, and you could say as a base class, if you will, and you could have a class called the dog, which maybe extends from pet, if you will. So you can come down here and say, you could say new dog, and the dog person is going to have a dog as a pet. So when you invoke this method, obviously, the play method here is going to call the getPet method, but the getPet method that you see up here is abstract, but because of polymorphism, that's going to call the method here on the dog person, which can then return the object. And similarly, you can create one for the cat as well. For example, for a cat lover, so you could potentially write different functions. But the idea here is, if you are using a factory method pattern and you're wondering, how could you use a factory with interfaces? Well, the abstract methods of interfaces could become those factory methods. You can provide common functions as default methods in the base interface, and then you can start overriding them in the derived classes as well. I've used this approach quite a bit when I find that I don't quite need a class to be created in the base because I don't want an abstract class. I don't want to put a field implementation in there. I may want to vary the way I implement the field. This gives me a nice opportunity to not have an implementation or a state in the base, but have the implementation of the state in the derived, which is exactly the point here, is that you have the ability to write the functions up here without really binding yourselves to a implementation detail. The implementation is completely removed from the base, and when you call the abstract method, that then can tie down to an interface, that then can tie down to an implementation rather, and we can use that in here. So that gives a nice way for us to create this abstraction with no implementation, but the implementations are completely pushed down to the derived classes or to records if you want to use records. That can become really, really powerful, as you can see. So that gives us an opportunity to dive in a little bit more into using a few things for lambda expressions before I go into something a little bit beyond that. So let's talk about the decorator pattern just a little bit, if you will. I think most of us have actually probably looked at decorator pattern at some point in time. But remember that infamous example of the decorator pattern. If I may recollect your memory on it, you would say new may be a buffered, maybe a data input stream, and then a new buffered input stream, and then a new file input stream, and then, of course, you provide other details for it. Anyone remembers that example that you saw before? And you look at this and you're thinking, oh my goodness, this is really scary, and it only gets worse with all these new, and new. And then you kind of wonder, and you look up the dictionary, maybe the word decoration means to make things ugly. And we don't really have faith in the decorator pattern after that, isn't it? And so most of the time we kind of run away from this. And this is one of the most beautiful patterns, but I think it's very underutilized. But what is really this pattern? This is a very powerful pattern because it really gives us the ability to do the following. You can actually take a core behavior or capability and add different, you could say, different flavors. Flavors or skin based on what the users, you could say, of this abstraction really want. So you can say you want to really take a very core capability, but you want to really add skin or flavor to this capability. That's what a decorator pattern really provides it. Now, my mind is corrupted. Every time I look at something, it always relates back to software design or programming. But I'm a big fan of outdoor natures as well. But anytime I'm outdoor hiking the mountains, I would see somebody with really a fancy camera. And when I see them with the fancy camera, unfortunately, I always think of the decorator pattern. Because you have these people have a really nice camera, but then they have these lenses. And they would be taking a photo of something. Maybe they want to take a photo of something at a distance, or they want to take a photo with a certain, filtering. So what do? They remove their lenses, they put them away, they take other lenses and they put them on, and then they take a photo. While they're enjoying the nature, I always think of the decorator pattern. Those little lenses or those skins or the flavors that you are able to add to the core camera. So you don't have to carry multiple cameras. You carry one camera, but you carry multiple lenses. So that's the whole idea of a decorator pattern is you can take the core, but you can keep varying the parts, and the user decides what combination to bring in and what to change over time. But the point is, how can we enjoy that kind of decoration, but without a smelly code like the one we saw? Because this really feels like really a very heavyweight solution. And secondly, if you again think of the decorator pattern with the camera as an example, your camera is an object. It is doing some real work with whatever processing it needs to do. But you can think of these filters as merely functions, because these filters are really transformers. They are taking the light that comes through, do some processing on the light, and they pass it on. So they are really purely functions, and you want to really combine those functions together. That's what you're really trying to do. So let's entertain this thought here to see how we can enjoy something like a decorator pattern right in here. So let's start with a little import, let's say a awt.color, just to bring in a bit of a color here. Here is a class called a camera, let's say. And within this camera, I want to provide a function, let's say in this case, color snap, and that's going to take a color as an input. So all it's going to do trivially right now is to simply return the input given. We'll evolve this code in the next several minutes as we work through it. So now I have a public, let's say in this case, a print, which takes a camera. I'm going to bring this in as an object right here, and I'm going to simply say right there, output camera.snap, and I'm going to provide a new color. Let's just keep it to 125, 125, and 125. So let's just call with that particular function. So let's give it a try right here. So we can call the print function new camera, and we can pass to it. And in this case, as you would expect when you call this with a camera right there, what you're noticing here is that this camera is going to take the input and return the output. So the color is 125. So that's a very simple first step in the code. However, I want to really apply a filter. When I use the word filter here, I'm using the word filter like in a camera's filter, not a filter in functional programming at this point. So a filter really is going to take the little light that comes through and perform certain transformation. Incidentally, the filter is more like a mapping function in the case of a camera. So how do I bring in that filter and use it in this particular case? So what I could do is I could start with, let's say, a function to begin with. So we'll bring in a function right there. And this is going to take a color as an argument. And it's going to return a color as an argument. And we'll call it as a filter like so. Let's take baby steps right here. So what I can then do is come back to this code and say filter.apply, and I can pass the input to it and perform the apply like so. And just for now, let's go ahead and say this is going to be input is going to be going to be the output. So that's my initial filter I start with. So if I were to run the code, you can still see the color is 125. However, I could now provide a camera with no argument constructor. I can also provide a camera with a function which takes a color and returns a color, and we'll call it as a filter. Well, and then of course in this case you could simply say this dot filter is equal to filter, and you can bring that in as a filter. So as a result now, you could go back to this and say, well, given a input, I want to return an input dot brighter, maybe. We'll make it a brighter color. And this is going to brighten up the color, if you will. So 125 became 178. Or, as you know, you could simply replace this with a color, and you can just simply pass a method reference to it as well, so that becomes a lot easier to pass it. Well, that's a nice step, but where do we go from here? Well, we can now think about maybe sending in not a brighter, but a darker as well, and you can see that the color is darker. But you know where I'm going with this. Maybe you want to mix multiple filters for whatever reason you want to. So what you can then do here is you can make a slight modification to this. You can take the filter that's in here, and you have an input given an output. We'll come back to this in just a minute, if you will. But here is one beautiful feature that I really like in functional programming and in Java as well. And that beautiful feature is, let's think about this for a minute with a little example here, if you will. So this particular feature is where, suppose you have a function given to you. Let's say this function is taking an integer and returning an integer. We'll call it inc is equal to, given an element, return an element plus 1. Similarly, I have one which is called double it, which is going to double the value, let's say. So the beauty of this is you can take these two functions, if you will, but here's something you can do nicely. You can say, given this integer, returning an integer, and you can say combined is equal to, and you can say inc and then, and you can combine it with the double it like so. So this gives you a function that can combine functions together. So in other words, the idea is, in generally speaking, we do object decomposition. For example, if I show you a pen and I ask you, what is that? You're going to say, gosh, that's a pen. But I can start removing the pieces of the pen into these multiple pieces. And then I can put them back together as a pen. And we know that's object composition. You can aggregate objects to form bigger objects. In a similar way, you can aggregate functions to form a bigger function as well. And so that and then combines the two functions together to create a bigger function. So in this particular example, if you will, what's going to happen with the combined is, the combined is going to be a function that actually takes the data, sends it to an increment function, takes the output of that, and then sends it to the double it function, and then takes the output of that, and then of course returns that output to us, the caller. So that becomes your combined function, where it really chains those functions together internally, which is a very powerful concept of function composition, which we can make use of really nicely for our purpose as well. So what I'm going to do in this particular code example is, I'm going to go back to this code and say, hey, let this camera receive not just one filter, but let it receive filters. So by changing this into a var arg, you can pass 0, 1, or any number of arguments to it, so that gives us a bunch of filters, if you will. So going back to this, here is a filter, and I can come back here and say a filter is input, and that gives us an input as an output. Then you can say a var, you could say a filter, and the filter comes in from the filters, if you will, and you can say filter is equal to filter, you could say, and then a filter, and you can combine that together. So essentially, in this case, when a collection of filters is given, you are able to form one filter, but that filter is actually a chain of filters that you can combine together using the and then. And once you combine them into a filter, a sequence like so, what are you going to do with this now? You can come and apply that filter chain very nicely up here. So as you can see, the code is working, but the beauty of this is I can now go back here and I can say a color brighter, comma, a color darker. So you are now able to apply two of the filters right there, and when you run the code, as you can see, the result is 124 because it's combining the two filters together to put them in here. So this is a nice, interesting way to combine these operations for decoration. Now, in this example, my filters were doing a brighter or darker, but think about this a little bit further, if you will. You can think about these as policies you implement in your code. You could have, for example, a masking, one that cleanses the data, one that is going to transform the data to something else, one that performs unit of measure conversion. You can start putting any combination of these things together, and your users can use those combinations as decorators. As one small detail, which doesn't really change what we have done so far, but just pushes this a little bit further in terms of conciseness of code, you can look at this code and say, maybe there's a way to write this code in functional style. Anyone can see what function you might use for this? Bingo, awesome. Reduce function, you nailed it. That's exactly what it is. It's a reduce operation. So what you can do here is you can take this code and perform one small refactoring. What you can say here is you can say a filter is equal to, and I'm going to bring in the stream right here. So we'll say stream. And so filter is equal to, you can say a stream of filters, if you will, and then dot reduce, and so we took care of the reduce for the for loop. And what are we going to do? The initial value we want to start with is, given an input, I want to return an input back to the caller, so that becomes that particular call. Hey, what about the and then function? Well, you can now say, in this particular case, combine the filter, comma, a filter, and you can simply say this becomes a combined filter and then a filter, and you can combine it like so. So this becomes a nice way of using reduce function. Well, that's kind of nice, but then you can say, oh, but this input and input really is nothing but your function dot identity, because an identity function returns the input given to it. So that's an identity function. So that takes care of it. And as a final refactoring, you can take all of that out and simply say function, if you will, and then double colon, and then, and you can simply use a method reference for it as well. So that becomes a little nice refactoring to use a reduce function in here, as you can see. So this becomes an interesting way to implement the decorator pattern. And of course, to use the decorator, you are able to just simply pass those functions or method references rather than having to write monstrous new and new and new. You're not using classes and objects anymore. Your decorators are simply functions now that you're able to use to form the decoration. The code is very concise as well for the creation of the decoration, but also to use the decorator as well, as you can see in the bottom right there. So that's an example of how we can make use of the decorator pattern. Well, I want to now give you two more examples here in the time we have. One is about the execute around method pattern, and this is a pattern that has been kind of introduced in stages, if you will, but we can go a lot further with this. Suppose we have a class called resource, where the class resource contains, let's say, an external resource of some sort. So we'll say, let's call this as create external, stuff. So that's going to use an external resource. But then I'm going to provide op1, and all that the op1 says is performing op1, and let's say it returns a current object. Similarly, I'm going to say here is an op2 function, which is going to simply say op2 and return the object. But if I were to create a resource, let's say resource, and I'm going to say equal to new resource, and I have a resource.op1 being called right there, and I also call the resource dot, let's say, op2 in here as well. But the question is, what about the external resource we created? Don't we have to get rid of it properly? Well, here's the good news. Java has automatic garbage collection. But the bad news is garbage collection is automatic, but it's not instantaneous. You don't know when it might actually be called. Well, in the past, what we tried to do was to write the finalize methods. So we would write, for example, public void finalize, and within this method, we could say clean up the, you could say, external stuff, and you could write the code like that. But unfortunately, though, in this particular case, what we are going to notice is that that function is not going to be called, unfortunately, in this particular case. So what is the reason for it? Well, the reason for it is, let me fix this error right here. So the reason for it, obviously, here is that the finalize method, while present, the garbage collector says, I've got a lot of memory, I don't need to be collecting garbage right now. So as a result, the automatic garbage collection is postponed, and in the meantime, you got resources that are accumulating. Not a very good situation to be in. Well, it turns out this was not a great idea. So as a result, finalize was deprecated in Java 9. So you would get a warning, but generally in my case, I treat warnings as errors, so my build will fail if there is finalize being called anywhere in the code. So the question is, what do we do to handle this problem? Well, you could write a close method if you want to, which is great, but then, who calls the close method? And Java has the try with resources. I'm not a fan of try with resources, honestly. The reason is you still need to remember to use the try with resources. If something is really critical that it get cleaned up properly, I would rather be done properly by the author of the class. So I'm going to go beyond the try with resources to implement this code. So what I'm going to do here is to write a close method, but the close method is going to be a private method, as you can see. Similarly, I make the constructor private as well, so you cannot create an object of resource anymore. That code actually fails. So then what I'm going to do here is to write a public, let's say, static, and I'm going to write a use method, which takes a consumer of resource. We'll call it block as an argument, like so. So we are bringing in this particular case, a consumer for the use method. Then I'm going to say resource, let's say, is equal to new resource, but I'm going to write a try and finally block because I can then remember to do the proper cleanup. and I say resource.close, and I'm going to close that. But then within this, I'm going to say a block, and I say block.accept and pass the resource to it like so. So this gives an opportunity for us to take the use method, pass a block of code to it. It creates the resource. Then it calls the block right there. And then when it comes back dead or alive, it performs the close operation. So the benefit of this is you can simply use the use method right now, receive a resource like so, and then now you can say resource.op1, and you can call the resource op2 on it. And then, of course, when you're done with it, you could simply close that particular section. So the benefit of this particular solution is this gives you what's called the execute around method pattern. So in other words, you want to write some code, but around that code, you want to perform a pre-op and a post-op. The place where I've used this very effectively is when I wanted to perform a certain piece of code within a transactional context. So my code creates a transaction, calls into my code to do whatever I want to do, and when my code returns, it either commits the transaction or rolls it back depending on any errors. So that can be a very streamlined operation you can perform in your code, and so this becomes a very effective way. So this particular approach is very popular in a lot of languages. They use, for example, to open a file, but you don't have to remember to close a file. The file gets closed automatically. You can use an external resource, and when you're done with using the resource, you leave the block of code, it automatically closes the resource. This, I would argue, takes the idea of try with resources to the extent where you don't have to worry about forgetting things. It really makes it happen because the code is designed that way. That's the benefit you get out of this execute around method pattern. And you can use this for so many different things in your code to implement various policies, things that you have to check before you enter a piece of code, things you have to validate, a pre-op and a post-op. That's basically what it provides for you very effectively. So the last pattern I want to talk about here is there are times when we want to restrict objects to, in a hierarchy, to a certain objects you want to use. For example, in some of the projects I worked on for my clients, there are times when they provide an interface and they want their users of their code to use the interface, but they never want the users of their code to implement those interfaces. So in other words, they want to have a handful of implementation. They want the users to use the interface, but not implement or override from that interface. That is incredibly hard to implement in Java previously because that takes a lot of coding that we have to do ourselves. That's error prone, more code to write, becomes clumsy, and often we don't get a compilation error as well in spite of all that effort. So here is an example of how we can achieve that right here. So to understand this, let's create a traffic light.java. So where we create an interface, let's call this as an interface called traffic light. And now I have a, let's say, public final class called red light, where that implements, in this case, the traffic light, as you can see. Similarly, I have a yellow light, and then, of course, I also have a green light here as well. So in this case, we have 3 different implementations of this particular interface. But I'm going to mark this interface as sealed, as you can see right there. So when I mark this interface as sealed, Java says these are only the inheriting members of that particular interface. They call it sealed classes, but you can use this for sealed interfaces as well. So now what I can do here is make use of this. I can say traffic light, and we can say, traffic light is equal to new red light, for example. I can create this and I can print out the traffic light here like so if I wanted to. And in this case, of course, it's in the same file, so I wouldn't make that as a public. So go back and run the code, and you can see the traffic light. However, the benefit of this is, suppose I were to create a class, you will even say a final class, let's say a broken light. And it implements, in this case, a traffic light like so, that's not permissible. You get an error. What's the error? It says class is not allowed to extend a sealed class. Well, you cannot write a broken light. Why? Because that's a sealed class or a sealed interface. Its members are restricted. Of course, as this is a special case, you can also use a permits clause, and you can say what are the implementations that they permit, and you can provide those permits as well to provide that kind of capability. So this gives you an idea how you are able to create a closed hierarchy of classes or interfaces, and you can say, my members are restricted to this, and the compiler will guarantee that for you. Those particular implementations are required to be in the same package if you're not using Java modules, and if you're using Java modules, they could be in any package, but they are required to be in the same module as well. So you have a better control on the hierarchy. When you do this way, the users of your interfaces are happy to use your interface, but they don't have permission to actually create an implementation, and that is controlled by the compiler, as you can see. So we looked at a number of different ideas that we can implement in design. As the language evolves, a lot of these become features of the language, as I mentioned, so we can enjoy them without really having to focus them as separate patterns. If you're interested in downloading the code examples, they're available on my website. Hope that was useful. Thank you so much.